Thank you very much. So I have my talk about a paper I wrote about the detection of fetal aberrations from shadow sequencing of maternal plasma based on a within sample comparison scheme. So to actually explain the title for a bit, I want to start with what kind of aberrations are we actually looking at. So I have a little example on the next slide. This is a case of a child with Down syndrome, and it's caused by having one additional chromosome 21. So the kind of aberration we're looking at is a duplication of a whole chromosome, and it's just this kind of aberration we're looking at, so copy number variations. And the point is that whenever a woman is pregnant of, well, a child, then she probably wants to know whether the child is healthy or not, and there's quite large chance to have a child with Down syndrome relatively to having a child with other disorders. Until now, it was possible to assess the risk of having a child with Down syndrome, and whenever a woman has an increased chance of having a child with Down syndrome, she might opt for invasive procedures, and the invasive procedure would be to use a needle and sample a little bit from the womb. Then you can use this little sample under a microscope and see whether the baby will have, say, an additional chromosome. Downside of this method is that it's very painful for the woman, and also it brings a slight chance of miscarriage. So you might lose your child in the process of actually trying to figure out whether it's healthy or not. So lucky for us, someone found out, I think 16 years ago, that there's a slight amount of fetal DNA floating around in the maternal bloodstream. So in addition to a lot of maternal DNA fragments, there's also a small proportion of fetal DNA fragments. And we believe this is about 5 to 20% in most cases. Sometimes it's a lot more, and sometimes it's far less. It also kind of depends on how heavy the woman is and some other factors. And well, the point is that with the recent upswing of next generation sequencing, we're able to sequence these little fragments of DNA. And what you end up with is what we often refer to as a very big box of puzzle pieces. And if you use a computer, you put all these pieces of the puzzle back together according to a reference, and you end up with some kind of a picture of what this person looks like you're sequencing. In our case, we have a woman and a child in the data set, so we would kind of expect to see a picture like this. But in reality, the woman and her child are actually on top of each other, and we have no idea which part of the fragments we found is actually from the child or from the woman. To make things even worse, the machine we're using has its own influences on what kind of reach we find. People in the lab and their chemicals have their influences, and even if we replace them by robots, then nature will find a way to add more noise to our data. So you end up with a figure like one in the middle, and the question that says, well, is the baby okay? Honestly, I don't have a clue if I look at a picture like this. So someone came up with a method previously to figure out the Down syndrome case, and he said, well, if you just take the relative amount of reads mapped to chromosome 21, and you compare this amount to a set of reference samples that's also in the same run, then you can say, well, the amount of reads you found in chromosome 21 is much more than we would expect to find if this child were to be normal. So we use the z-score and say, well, it's 3 times the standard deviation away from the mean of the reference set, so okay, we have an aberration here. And this method works very well for chromosome 21, but it has a few downsides. First of all, it doesn't work for any of the other chromosomes, as far as we know. It's also not very stable for subchromosomal aberrations, as well as very prone to experimental differences. And because of this, we need to run a few reference samples for every time we want to know whether someone has Down syndrome or not. So that's very costly. And our idea was that within a sample, these technical variations occur across the whole genome. So we could use regions within a sample to compare with other regions in the same sample as a reference, leaving out all the experimental effects we have in the above. After that, if we know these kind of regions, we can simply test for aberrations by comparing within the sample. And to do this, we decided to split the whole genome into subchromosomal regions. After doing that, we can simply determine reference regions in the genome based on, well, the variations in a set of healthy samples. And when we know these reference regions, we can simply test a sample we get by comparing each region in the sample to its set of reference regions within the same sample. Therefore, we have to within the sample comparison method. So the implementation of this was basically we split all the chromosomes into 1 megabase bins, so each area is just a set area. And we determine the amount of reads mapped to this area relative to the total amount of reads we have, so the read frequency per bin. And we apply a GC correction to get rid of most of the variations in the samples. After that, we can simply determine the difference between every target bin and every other bin on either other chromosome we have. And we square this difference, so you have very heavily penalizing so you are very heavily penalizing large differences within a few samples. So you do this over all your healthy samples, and you can add the different values together, and you end up with a sequence of values that tells you which bins are most alike and which are not. So in this example, we could simply pick, for example, the first bin, because it has very small values, so it's very much behaving alike. This bin in chromosome 2 is very much behaving alike the red bin in chromosome 1 in the middle. One little detail in this place is we ignore neighboring bins, so the 2 bins mostly to the right, only one of them is picked as reference, because otherwise you may be very dependent on a certain region on your genome, and if this other region is aberrated, then you cannot find any aberrations in your current target bin anymore. So we repeat this for every bin on every chromosome, and you end up with a very large reference table that tells you where to look for reference regions for any time you want to test one bin on your test sample. To give you a little bit of a visualization of what we have created so far, I've plotted all the autosomal chromosomes in a circle, so on the outside you see chromosome 1 up to 22. And we drew a little line, a black line from every target bin on chromosome 21 to each of its reference bins on all the other chromosomes. And the interesting thing in this picture is that chromosome 19 is not very well playing along. And the reason for this is that chromosome 19 has different chemical properties. It's behaving differently on the machine. So it was kind of to be expected that this one would not be, well, selected a lot for reference bins for chromosome 21. So next up we can start testing samples, and to do this we just take every target bin in the test sample. We collect the values in the set of reference bins for this target bin from the same sample, and we just compare the value we found to the set of reference values we have within the sample. The problem is that if you just apply the z-score on this one bin, is that the signal from the child, so the fetal DNA, is quite small, so you do not always have enough deviating scores to actually call the aberration whether it's there. Also, whenever the mother has an aberration, so a very short spike, she may have duplication somewhere within the bin, and therefore you can end up having a lot of single bin false positives. To get around these problems, we decided to combine several z-values together. So we apply a windowed z-score, where we just take the z-scores from the previous step, combine them together using the Straver's z-score, and that way we have a much stronger sensitivity for a series of deviating bins. As a little example of this method, I drew a little table, and on every column we have a target bin for, say, a certain sample. And right below there we have a whole set of reference values for each of these target bins. And based on these reference values, we can determine a mean and standard deviation for what we would expect to find in this target bin, compare it to the actual value for this bin, and use the z-score to score this bin's z value. And whenever it's over 3, the absolute value is over 3, we call it an aberrated bin. Now you may run into a little problem, because if you do this right away, then you actually may have aberrated bins in your reference set. So what we do is whenever we find one bin to be strongly aberrated, we remove it from every reference set we have during the test for this one sample until we do not have any more of these reference aberrated bins in our reference set anymore. After we've done that, we can combine multiple z-scores together with the windowed z-score approach, and we score the one bin in the middle with the summed z value after we left out the lowest and the highest value to remove very strong spikes in our data. So what comes out of our method is also a little nice plot, because a bunch of numbers is not very informative to people. And it's a bit of a difficult to understand plot, so I will explain what you're looking at first. So on the left we have the short arm of the chromosome, and on the right the long arm, so we're actually looking from base pair 0 to the very end of the chromosome from left to right. And the centromere is the little gray area in the top figure in the middle. By accident, I didn't put it up there. The blue line is the single bin Z scoring method, and as you can see it's going up and down all the time quite a bit, while the red line is the windowed Z-score, so it's the combination of this blue line over a window. Now these gray areas actually mean that we do not have a lot of information to make any calls on this area. So the light green ones say, okay, light gray ones say, I did not have a very stable reference set to make any calls on this bin, while the dark gray one says, well, I've never seen any read map to this area in my reference set, so I have no clue what's happening here. And whenever we find a bin to be aberrated with a single bin z-score, we make a little green block on the bottom. And whenever it's part of a large series of aberrated bins, we make it dark green. While on the top side, we add a little pink area whenever we find it to be aberrated in the windowed z-score method, and we apply it in dark purple whenever it's part of a sequence. So what you find if you apply this method for all chromosomes within one sample with Down syndrome, you end up with something looking like this. Pretty much all the chromosomes looks completely fine, except for chromosome 21, which has been found to be aberrated over the whole length of it. With chromosome 21 was already done using the z-score previously, so we're more interested in other cases. And for example, chromosome 7 is one of the things that popped up lately. It's a bit of an interesting one as well, because usually the child doesn't really have a problem if you have chromosome 7 trisomy. It may happen that it's just the placenta, or it's just that the child may recover from it somehow. I'm not very sure on the biological reasons for this, but apparently it's not that important. On the other hand, we also have chromosome 13, which was a problem previously, and we actually are able to find it completely aberrated. While you can see that the single bin method does have a bit of a problem on calling it, and therefore the windowed method is doing a much better job on recognizing the aberration here. The same goes for chromosome 18, or trisomy 18 actually, while trisomy 22 is not actually really a problem, it's a very stable chromosome. Even more interesting than this is we can also find subchromosomal aberrations. So in the top one we have isochromosome 12. This fetus has 2 additional short arms of chromosome 12. And as you can see, only the short arm just before the centromere is found to be aberrated, while the long arm is completely okay. Another interesting find is a deletion on chromosome 13, somewhere in the middle, and considering we previously had a hard time calling trisomy 13, it's quite impressive we have been able to find a deletion in the subpart of chromosome 13. And last, I also have a case where the short arm of chromosome 18 was replaced by an additional long arm. So if you would look at the whole chromosome score, you would actually cancel each other out a little bit. And my method was able to detect both of the aberrations in this case. So taking all of this together, we have shown that it's possible to find both chromosomal as well as subchromosomal aberrations. And we do not actually need to rerun healthy reference samples for every time we need to test a sample. And we can all do all of this using very affordable low coverage NGS. So only 12 to 14 million reads is enough. And these reads are just single end reads. And this is based on plasma obtained from maternal blood, so it's a very safe method, and the woman only has to go to the hospital to give a little bit of blood, and that will be enough to determine most of these fetal aberrations. And as a result of this, the method is actually applied in most of the Dutch medical centers right now as a prenatal screening test to determine whether someone has child with an aberration, saving a lot of the invasive tests. And before we end this presentation, I would like to make you aware of a little problem. We also find maternal copy number variations, and this is mostly a bit of an ethical problem because a woman goes to the hospital and asks, is my baby okay? And now you start running these kind of tests and you end up seeing that the mother may or may not have a problem. And now the ethical question becomes, do you have to report these kind of aberrations? Because this is not what she asked for, but you might be able to help her if she knows. And even worse, if someone would have cancer, you probably see duplications all over all the chromosomes, and this is not what people ask for, but we can see it this way. So, that being said, I would like to thank everyone who helped me in the process of this project, and I would be happy to take any of your questions. Thank you very much.
It's wonderful work. I do have a question. So you must have validated this in some way with sensitivity and specificity for it to be adopted clinically, but you didn't present that.
I didn't present the numbers indeed. The point is when I was working on this project, I only had like 60 samples, I think, and most of them had aberrations. So I just focused on actually finding those aberrations mostly. Before it was put into the diagnostic part, we had, I think, 250 samples run, and we tried to figure out whether we could find all the aberrations in 250 samples. The method found all of them and didn't make any wrong calls, so it's like 100 and 100%.
Great talk. Our company actually does NIPT. We're a San Diego-based company, Sequenom. So we also face very similar problems for microdeletion detection. So I was just wondering, to overcome the false positives, to get rid of the sequence noise is essential in the steps. So can you elaborate a little bit more on the data normalization procedure you use? Do you just correct for the GC bias, or do you do some higher order corrections? And the second question is, you're partitioning your genome into 1 megabase bins effectively. So what is the smallest CNV you can detect using the current technology? And do you do any size filter to avoid small false positives?
Yes, well, for the first question about GC correction, we just applied lowest GC correction, and that's it for the correction part. And most of the other corrections are basically incorporated by the within sample comparison method. So technical variation usually get caught by the within sample comparison. So it's not like I did not apply PCA or anything, if that's what you're referring to. And the second question was?
So the second question is the resolution of your method.
Oh, yes.
Yes.
I'm using 1 megabase bins, and we combine, I think, 11 bins together to make a windowed call. So you're pretty much forced to look at aberrations larger than 11 megabase. And I filter out anything smaller than, I think, 15 megabase, and we usually do not report anything smaller than 20 megabase.
I see. So do you guys have a plan to validate this method in a large blinded study, in a large cohort, to see the power of the method, returning to the earlier question, sensitivity and specificity, blinded fashion?
It's actually applied in diagnostics in a screening test, and our diagnostics currently, whenever you sign up for it, you're also applying for being part of say a large cohort, pretty much. So by the end of the year, I think, everyone we have tested we should know the answer. So at the end of it, we will know how many of them we actually missed and how many of them we correctly identified.
Thanks.
You said that you found copy number changes in the maternal. How can you tell if it's the maternal copy number changes or the fetus's copy number change? And does that affect your analysis when you see like the copy number change in the maternal sample?
What do you mean, does it affect my analysis?
Yeah, so I mean, if you saw a copy number change in the mother, you wouldn't necessarily see that copy change in the fetus, correct? And you could have, what, one copy number change in the mom, and she didn't pass that change on to the fetus.
Yes.
So how can you tell if the child, or like the fetus has that copy number change?
It's a good question. The point is that the image I show over here is only like 2 bins together. So, and if you look at the numbers down there, it's not spanning even more than 1 bin, so it's just a little bit in both bins. We have had, I think, 1 or 2 cases where it spanned multiple bins, so I think it was like 5 megabase of duplication in the mother. And because the method also, let me go back there. So we compared with these, the mean and the actual value. I can use these values to also determine how many times we actually, so the multiplication of this bin. So I can determine how many times I actually found what I should have been found. So whenever the mother has a duplication and the child has not, we expect this number to be about 1.47 or 1.45 pretty much. Well, if the child would have received the same duplication as well, it's probably about 1.5 or something. It's just a bit of guessing because I do not have enough data for that yet. So I'm not filtering it out.
Thank you for a very nice talk. One issue in these methods is the amount of fetal material present in the maternal sample. So do you actually try to assess the fetal fraction? And if so, is there some floor below which this method doesn't work?
Could you repeat the last sentence, please?
I was just wondering if there's some floor, if the fetal fraction is too low, like where does this break down?
As far as I understood from my colleague, who is actually running these tests all day, I think she said the bottom line is like 4 or 5% of fetal DNA. And my method just assumes there would be enough fetal DNA to actually determine the aberrations. And when we applied in our diagnostics, currently we're just trying to tell the boys from the girls based on the amount of reads mapped to the Y chromosome. And if we fail to do that correctly, we kind of know that there's probably something wrong with the run. But this in no way ensures that we can also say the same thing about the girls, because girl samples we cannot determine anything about. And there have been several proposed methods to actually determine the fetal fraction, say using C-methylation, which, well, the data I've seen is just all over the place, so it's not very reliable. Mm-hmm. And I believe Dennis Lowe published a paper a few months ago about using paired end sequencing, so we could determine the fragment length. And because the child has, well, smaller fragments, they could determine about the fetal fraction, but we're not using that one yet.
Okay, thank you.
Yep.